Learning objectives. In this chapter, the user would learn the following in detail: stochastic processes and specifications, stationary processes, Markov chains, Markov processes, Poisson process, renewal process, birth and death process, random walk, Brownian motion. Birth and death process. We consider pure birth process where probability of number of births between t and t plus h is k, given that the number of individuals at epoch t is n, is given by probability of k, h such that n, t equal to lambda n into h plus order of h, where k equal to 1, then order of h where k greater than or equal to 2, then 1 minus lambda n into h plus order of h, where k equal to 0. The above holds for all n greater than or equal to 0, lambda naught may or may not be equal to 0. Here k is a non-negative integer, which implies that there can only be an increase by k, that is, only births are considered possible. Now we suppose that there could also be a decrease by k, that is, deaths are also considered possible. In this case, we shall further assume that probability of number of deaths between t and t plus h is k, given that the number of individuals at epoch t is n, given by q of k, h such that n, t equal to mu n into h plus order of h, where k equal to 1, then order of h where k greater than or equal to 2, then 1 minus mu n into h plus order of h where k equal to 0. The above holds for n greater than or equal to k. Further, mu not equal to 0. We have what is known as birth and death process. Through a birth, there is an increase by 1, and through a death, there is a decrease by 1 is the number of individuals. The probability of more than one birth or more than one death in an interval of length h is order of h. Let n of t denotes the total number of individuals at epoch t starting from t equal to 0, and let Pn of t equal to probability of n of t equal to n. Consider the interval between 0 and t plus h. Suppose that it is split into two periods. In the open interval 0, t and the closed interval t, t plus h, the event n of t plus h equal to n, n greater than or equal to 1, having probability p, n of t plus h can occur in a number of mutually exclusive ways. These would include events involving more than one birth and or more than one death between t and t plus h. By our assumption, the probability of such an event is order of h. There will remain 4 other events to be considered: aij, n minus I plus j, individuals by epoch t, I, birth and death between t and t plus h, I, j equal to 0, 1. We have probability of a00 equal to Pn of t into 1 minus lambda n into h plus order of h into 1 minus mu n into h plus order of h equal to Pn of t 1 minus lambda n plus mu n of h. That means we have to write lambda n plus mu n inside the bracket plus order of h. Then probability of a10 equal to Pn minus 1 of t into lambda n minus 1 h plus order of h into 1 minus mu n minus 1 h plus order of h equal to Pn minus 1 of t into lambda n minus 1 h plus order of h. Probability of a01 equal to Pn minus 1 of t into 1 minus lambda n plus 1 into h plus order of h into mu n plus 1 into h plus order of h equal to Pn plus 1 of t into mu n plus 1 into h plus order of h. And probability of a11 equal to Pn of t into lambda n h plus order of h into mu n h plus order of h equal to order of h. Hence, we have for n greater than or equal to 1, Pn of t plus h equal to Pn of t into 1 minus lambda n plus mu n into h. That means lambda n plus mu n is inside the bracket, plus Pn minus 1 of t lambda n minus 1 h plus Pn plus 1 of t mu n plus 1 h plus order of h, or Pn of t plus h minus Pn of t divided by h equal to minus of lambda n plus mu n into Pn of t. That means lambda n plus mu n should write inside the bracket, plus lambda n minus 1 into h into Pn minus 1 of t plus mu n plus 1 into Pn plus 1 of t plus order of h divided by h. And taking limits as h tends to 0, we have Pn of t equal to minus of lambda n plus mu n inside the bracket, Pn of t plus lambda n minus 1 into Pn minus 1 of t plus mu n plus 1 into Pn plus 1 of t, comma n greater than or equal to 1. For n equal to 0, we have P naught of t plus h equal to P naught of t into 1 minus lambda naught into h plus order of h inside the flower bracket, plus P1 of t into 1 minus lambda naught into h plus order of h inside the flower bracket into mu1 into h plus order of h, this also inside the flower bracket, equal to P naught of t minus lambda naught into h into P naught of t plus mu1 into h into P1 of t, or P naught of t plus h minus P naught of t divided by h equal to minus lambda naught into P naught of t plus mu1 into P1 of t plus order of h divided by h. Hence we get P naught of t equal to minus lambda naught into P naught of t plus mu1 into P1 of t. If at epoch t equal to 0, there were I greater than or equal to 0 individuals, then the initial condition is Pn of 0 equal to 0, comma, n not equal to I, comma, Pi of 0 equal to 1. The equation or the equations of the birth and death process. The birth and death process play an important role in queuing theory. They are also having interesting applications in diverse other fields such as economics, biology, ecology, reliability theory, etc. Birth and death rates. Some particular values of lambda n and mu n are of special interest. When lambda n equal to lambda, that is, lambda n is independent of population size n, then the increase may be thought of as due to an internal source such as immigration. When lambda n equal to n lambda, we have the case of birth. Lambda n into h equal to n lambda h may be considered as the probability of the birth in an interval of length h, given that n individuals are present. The probability of one individual giving a birth being lambda h, here lambda not equal to 0. When mu n equal to mu, the decrease may be thought of as due to a factor such as emigration. When mu n equal to n mu, we have the case of death, the rate of death in unit interval being mu per individual. Particular cases. Roman letter 1. Immigration - emigration process. For lambda n equal to lambda and mu n equal to mu, we have what is known as emigration process. The process associated with the simple queuing model m bar 1 is such as process. Roman letter 2. Linear growth process. Generating function. In the Euler-Furey process, one is concerned with the population whose members can give birth only to new members but cannot die. Let us consider the case both births and deaths can occur. Suppose that the probability that a member gives birth to a new member in a small interval of length lambda h plus order of h, and the probability that a member dies is mu h plus order of h. Then if n members are present at the instant t, the probability of one birth between t and t plus h is n lambda h plus order of h, and that of one death is n mu h plus order of h, n greater than or equal to 1. We have thus a birth and death process with lambda n equal to n lambda, mu n equal to n mu, n greater than or equal to 1, lambda naught equal to mu naught equal to 0. Mean population size. We can obtain the mean population size by differentiating p of s comma t partially with respect to s and putting s equal to 1. It can however be obtained directly without obtaining p of s comma t. Using this, we can finally get m of t equal to I into e power lambda minus mu of t. Limiting case. As t tends to infinity, the mean population size m of t tends to 0 for lambda less than mu or to infinity for lambda greater than mu. Extinction probability. Since lambda not equal to 0, where 0 is an observing state, that is, once the population size reaches 0, it remains 0. Thereafter, this is the interesting case extinction of the population. We can determine the probability extinction as, suppose for simplicity that x of 0 equal to 1, that is, the process start with only one member at time 0, then p of s comma t equal to a minus bs divided by c minus ds equal to a1 minus bs given a divided by c1 minus ds given c, where a equal to mu into 1 minus e power minus of lambda minus mu t. Then c equal to lambda minus mu into e power minus of lambda minus mu t, and probability of x of t equal to 0 equal to p naught of t. The constant term in the expression of p of s comma t as a power series in s is given by a divided by c equal to mu into 1 minus e power minus of lambda minus mu t divided by lambda minus mu into e power minus of lambda minus mu t. The probability that the population will eventually die out is given by p naught of t as t tends to infinity and can be obtained from the above by letting t tends to infinity for lambda greater than mu, then limit t tends to infinity p naught of t equal to limit t tends to infinity mu into 1 minus e power minus of lambda minus mu t divided by lambda minus mu into e power minus of lambda minus mu t, mu by lambda less than 1. If lambda less than mu, then limit t tends to infinity p naught of t equal to limit t tends to infinity mu into 1 minus e power minus of lambda minus mu of t divided by lambda minus mu into e power minus of lambda minus mu of t equal to 1, and limit t tends to infinity pn of t equal to 0 where n is not equal to 0. In other words, the probability of ultimate extinction is 1 when lambda less than mu and is mu divided by lambda less than 1 when lambda greater than mu. Linear growth and immigration. In Roman letter 2, we have lambda not equal to 0, and as a result, if the population size reaches 0 at any time, it remains at 0. Thereafter, here 0 is an observing state. If we consider lambda n equal to n lambda plus alpha, where alpha greater than 0, mu n equal to n into mu, that is called n mu, where n greater than or equal to 0, we get what is known as linear growth process with immigration, where 0 is not an observing state. Subdivision 4. Immigration death process. If lambda n equal to lambda and mu n equal to mu, we get what is known as immigration death process. This corresponds to the Markovian queue with the infinite number of channels, that is the queue m bar infinity. Subdivision 5. Pure death process. Here lambda n equal to 0 for all n, that is an individual cannot give birth to a new individual, and the probability of death of an individual in t, t plus h is mu h plus order of h. Then if n individuals are present at time t, the probability of one death in t, t plus h is n mu h plus order of h. The birth and death process is a special type of continuous time Markovian process with a discrete state space 0, 1, 2, etc. Such, the probability of transition from state I to state j in delta t is order of delta t. Whenever modulus of I minus j greater than or equal to 2, in other words, changes take place through transition only from a state to its immediate neighboring state. Brownian motion. Relation to Wiener process. A Wiener process is a stochastic process with a similar behavior to Brownian motion, the physical phenomenon of a minute particle diffusing in a fluid. Sometimes a Wiener process is called Brownian motion, although this is strictly speaking a confusion of a model with phenomenon being modeled. A Wiener process is the scaling limit of random walk in dimension 1. This means that if you take a random walk with very small steps, you get an approximation to a Wiener process and less accurately to Brownian motion. To be more precise, if the step size is epsilon, one needs to take a walk of length L by epsilon square to approximate a Wiener length of L. As the step size tends to 0 and the number of steps increases proportionally, random walk converges to a Wiener process in an appropriate sense. Formally, if B is the space of all path of length L with maximum topology, and if M is the space of measure over B with the norm topology, then the convergence is in the space M. Similarly, a Wiener process in several dimensions is a scaling limit of random walk in the same number of dimensions. A random walk is a discrete fractal, a function with integer dimensions 1, 2, etc. But a Wiener process trajectory is a true fractal, and there is a connection between the two. For example, take a random walk until it's a circle of radius r times the step length. The average number of steps it performs is r square. This fact is the discrete version of the fact that a Wiener process walks is a fractal of Hausdorff, dimension 2. In 2 dimension, the average number of points the same random walk as on the boundary of its trajectory is r power 4 by 3. This corresponds to the fact that the boundary of the trajectory of a Wiener process is a fractal of dimension 4 by 3, a fact predicted by Mandelbrot using simulations but proved only in 2000 by Lawler, Schramm and Werner. A Wiener process enjoys many symmetries a random walk does not. For example, a Wiener process walk is invariant to rotations, but random walk is not, since the underlying grid is not. Random walk is invariant to rotations by 90 degrees, but Wiener processes are invariant to rotations by, for example, 17 degrees too. This means that in many cases problems on random walk are easier to solve by translating them to Wiener process, solving the problem there and then translating back. On the other hand, some problems are easier to solve the random walks due to its discrete nature. Random walks and a Wiener process can be coupled, namely manifested on the same probability space in a dependent way that forces them to be quite close. The simplest such coupling is the Skorokhod embedding, but there exist more precise couplings such as Komlow's major Tasnady approximation theorem. The convergence of a random walk toward the Wiener process is controlled by the central limit theorem and by Donsko's theorem for a particle in a known fixed position at t equal to 0. The central limit theorem tells us that after a large number of independent steps in the random walk, the walker's position is distributed according to a normal distribution of total variance sigma square equal to t divided by gamma t into epsilon square, where t is the time elapsed since the start of the random walk, epsilon is the size of the step of random walk, and gamma t is the time elapsed between two successive steps. This corresponds to the green function of the diffusion equation that controls the Wiener process, which suggests that after a large number of steps, the random walk converges toward a Wiener process. In 3D, the variance corresponding to the Green's function of the diffusion equation is sigma square equal to 6 into dt. By equalizing this quantity with the variance associated with the position of the random walker, one obtains the equivalent diffusion coefficient to be considered for the asymptotic Wiener process toward which the random walk converges after a large number of steps, d equal to epsilon square divided by 6 into gamma t, valid only in 3D. Remark: the two expressions of the variance above correspond to the distribution associated to the vector, that means our vector, that links the two ends of the random walk in 3D. The variance associated to each component Rx, Ry or Rz is only 1/3 of this value still in 3D. For 2D, d equal to epsilon square divided by 4 into gamma t. For 1D, d equal to epsilon square divided by 2 into gamma t. Gaussian processes. If the distribution x of t1, x of t2, etc. x of tn for all t1, etc. till tn is multivariate normal, then x of t, t belongs to capital T is said to be a Gaussian processes. Such processes derive their importance from the fact that there are many physical processes which are approximately normal. Example, the process describing atmospheric turbulence. Further, such processes have some very useful and simple properties. If a Gaussian process x of t is covariant stationary, then it is strictly stationary. The explanation is simple. The multivariate normal distribution of x of t1, x of t2, etc. till x of tn is completely determined by its mean vector mu1, etc. till mu_n. Then the covariance matrix C of I, j, whose elements are C of I, j equal to covariance of, inside the flower bracket, x of ti, x of tj, where I, j equal to 1, 2, etc. n. If the Gaussian process is covariant stationary, then expectation of x square of ti, expectation of x square of tj are finite, and the covariance function C of I, j is a function only of the difference I minus j. Example, let xn, n greater than or equal to 1 be uncorrelated random variable with the mean 0 and variance 1. Then C of n, m equal to covariance of xn, xm inside the flower bracket equal to expectation of xn into xm equal to 0, where m not equal to n. Then equal to 1 if m not equal to n. and so xn comma n greater than or equal to 1 inside the flower bracket is covariant stationary. If xn are also identically distributed, then xn comma n greater than or equal to 1, that means inside the flower bracket is strictly stationary. Poisson process. Consider the process x of t, comma t belongs to capital T with probability of x of t equal to n into expectation of minus at into at power n divided by n factorial, comma a greater than 0, comma n equal to 0, comma 1, comma 2, etc. We see that m of t equal to at, comma variance of x of t equal to at are functions of t. The process is not stationary. The distribution of the process is functionally dependent on t. Consider the process x of t equal to capital A1 plus capital A2 into t, where capital A1, comma capital A2 are independent random variables with expectation of capital AI equal to small ai. Variance of capital AI equal to sigma I square, comma I equal to 1, 2. We have m of t equal to A1 plus capital A2 into expectation of t. Then expectation of x of t into x of s equal to expectation of A1 plus A2 into t, comma A1 plus A2 into s equal to expectation of A1 square plus inside the bracket s plus t into expectation of A1 into A2 plus ts into expectation of A2 square equal to sigma 1 square plus A1 square plus inside the bracket s plus t A1 into A2 plus ts, that means t into s inside the bracket sigma 2 square plus A2 square. Then expectation of x square of t equal to sigma 1 square plus A1 square plus 2 into t into A1 into A2 plus t square into inside the bracket sigma 2 square plus A2 square. Then variance of x of t equal to sigma 1 square plus t square into sigma 2 square, and c of s comma t equal to covariance of x of t comma x of s equal to sigma 1 square plus t square into sigma 2 square. The process is not stationary. Markov process. If x of t comma t belongs to capital T, that means we have to write inside the flower bracket is a stochastic process such that give the value x of s, comma the value of x of t, comma t greater than s. Then do not depend on the values of x of u, comma u less than s. Then the process is said to be Markov process. A definition of such a process is given below. If for t1, comma t2, etc. till tn, comma t1 less than t2 less than etc. less than tn, probability of a less than or equal to x of t less than or equal to b, given that x of t1 equal to small x1, comma etc. x of tn equal to small xn. We have to write these things inside the flower bracket equal to probability of a less than or equal to x of t less than or equal to b, given that x of tn equal to small xn. This also want to write inside the flower bracket. The process x of t comma t belongs to capital T is a Markov process. Markov chain. A discrete parameter Markov process is known as Markov chain. Consider a simple coin tossing experiment repeated for number of times. The possible outcome at each trial are 2, head with probability say p and tail with probability q, then p plus q equal to 1. Let us denote head by 1 and tail by 0, and the random variable denoting the result of the nth toss by xn. Then for n equal to 1, 2, etc. Probability of xn equal to 1 equal to p, comma probability of xn equal to 0 equal to q. Thus we have a sequence of random variables x1, x2, etc. The trials are independent and the result of the nth trial does not depend on any way on the previous trials numbered 1, 2, etc. n minus 1. The random variables are independent. Definition: the stochastic process xn, n equal to 0, 1, 2, etc. that means inside the flower bracket is called a Markov chain, if for j, k, j1, j k minus 1 belongs to n. Probability of xn equal to k such that xn minus 1 equal to j, xn minus 2 equal to j1, etc. x naught equal to jn minus 1 equal to probability of xn equal to k such that xn minus 1 equal to j equal to pjk. Say, whenever the first member is defined, the outcomes are called the states of the Markov chain. If xn has the outcome j, the process is said to be at state j at nth trial to a pair of states j, k at the two successive trials. There is an associated conditional probability pjk. It is the probability of transition from the state j at the nth trial to the state k at n plus 1th trial. The transition probabilities pjk are basic to the study of the structure of Markov chain. The transition probability may or may not be independent of n. If the transition probability pjk is independent of n, the Markov chain is said to be homogeneous transition probability. If it is dependent on n, it is said to be non-homogeneous. Here we shall confine to homogeneous chains. The transition probability pjk refers to the states j, k at two successive trials. The transition is one step and a pjk is called one-step transition probability. In the more general case, we concerned with the pair of states j, k at two non-successive trials, say state j at the nth trial and state k at the n plus mth trial. The corresponding transition probability is then called m-step transition probability and is denoted by pjk power m. That is, pjk power m equal to probability of x n plus m equal to k such that xn equal to j. Transition matrix or matrix of transition probabilities. The transition probabilities pjk satisfy pjk greater than or equal to 0, summation k pjk equal to 1 for all j. The probabilities may be written in the matrix form p equal to p11, p12, etc. and then second row p21, p22, etc. Like this we can write third row, fourth row, etc. This is called the transition probability matrix or matrix if transition probabilities of the Markov chain. P is a stochastic matrix, that is a square matrix at non-negative elements and unit row sums. Probability distribution. It may be seen that the probability distribution of xr, xr plus 1, etc. xr plus n can be computed in terms of the transition probabilities pjk and the initial distribution of xr. Suppose for simplicity that r equal to 0, then probability of x naught equal to a, x1 equal to b, etc. xn minus 2 equal to I, xn minus 1 equal to j, xn equal to k equal to probability of xn equal to k such that xn minus 1 equal to j, etc. x naught equal to a into probability of xn minus 1 equal to j, etc. x naught equal to a equal to probability of xn equal to k such that xn minus 1 equal to j into probability of xn minus 1 equal to j such that xn minus 2 equal to I into probability of xn minus 2 equal to I, etc. x naught equal to a equal to probability of xn equal to k such that xn minus 1 equal to j into probability of xn minus 1 equal to j such that xn minus 2 equal to I into probability of x1 equal to b such that x0 equal to a into probability of x0 equal to a equal to probability of x0 equal to a into PAB etc. Pij into Pjk. Thus, probability of xr equal to a, comma xr plus 1 equal to b, comma etc. xr plus n minus 2 equal to I, comma xr plus n minus 1 equal to j, comma xr plus 1 equal to k equal to probability of xr equal to a into PAB etc. Pij into Pjk. Strong Markov property. Stopping time for a sequence of random variables x is a random variable. Let n be a stopping time for a Markov chain x, n greater than 0, and let a and b be two events relating to x and a happening prior and posterior respectively to n. Then probability of b such that x equal to I, a equal to probability of b such that x equal to I. This is called the strong Markov property. It shows that if n is a stopping time for a Markov chain x, n greater than 0, then the evaluation of the chain starts afresh from the state reached at time n. Strong Markov property is implied by the Markov property. Both the properties are equivalent when n is constant, a degenerate random variable. Every discrete time Markov chain x, n greater than or equal to 0 possesses the strong Markov property. Markov chains as graphs. Before we proceed to discuss classification of states, we explain how Markov chains can be described as graphs. The states of a Markov chain may be represented by the vertices, that means nodes of the graph, and one-step transitions between states by directed arcs. If I tends to j, then vertices I and j are joined by a directed arc with arrow towards j. The value of Pij, which corresponds to the arc weight, may be indicated in the directed arc. If S equal to 1, 2, etc. m is the set vertices corresponding to the state space of the chain, and A is the set of directed arcs between these vertices, then the graph G equal to S, A is the directed graph or digraph or transition graph of the chain. A digraph such that its arc weights are positive and sum of the arc weight of the arcs from each node unity is called a stochastic graph. The digraph or transition graph of a Markov chain is a stochastic graph. A path in a digraph is any sequence of arcs where the final vertex of one arc is the initial vertex of the next arc. The graph is called transition graph of Markov process. Example: a transition graph is of great aid in visualizing a Markov chain. It is an useful tool in studying the properties. Example: irreducibility of the chain. Poisson process. Introduction. Here we shall deal with some stochastic process in continuous time and with discrete state space, which, apart from their theoretical importance, play an important role in the study of a large number of phenomena. One such process is Poisson process, to which we shall confine ourselves here. To fix our ideas, consider a random event E, such as incoming telephone calls at a switchboard, arrival of customers for service at a counter, occurrence of accidents at ascertained places. Let us consider the total number n of t of occurrences of the event E in an interval of duration t. That is, if we start from an initial epoch or instant t equal to 0, n of t will be denote the number of occurrences up to the epoch or instant t, more precisely to t plus 0. For example, if an event actually occurs at instance at time t1, t2, t3, etc., then n of t jumps abruptly 0 to 1 at t equal to t1, from 1 to 2 at t equal to t2, and so on. The situation can be represented graphically as an f number n of t of occurrences of an event in an interval of duration t. The values of n of t given here are observed values of the random variables n of t. Let Pn of t between the probability that the random variable n of t assumes the value n, that is Pn of t equal to probability of n of t equal to n. The probability is a function of the time t, since the only possible values of n are n equal to 0, 1, 2, 3, etc. Summation n equal to 0 to infinity Pn of t into t equal to 1. Thus, Pn of t represents the probability distribution of the random variable n of t for every value of t. The family of random variables n of t, t greater than or equal to 0 is a stochastic process. Here the time t is continuous. The state space of n of t is discrete and integral valued, and the process is integral valued. One of the most important integral valued process is Poisson process, which serves as a mathematical model for a wide range of empirical phenomena with remarkable accuracy. The justification for this is based on the concept of rare events. We proceed to show that under certain conditions n of t follows Poisson distribution with a mean lambda t, lambda being a constant. In case of many empirical phenomena, these conditions are approximately true, and the corresponding stochastic process n of t, t greater than or equal to 0 follows the Poisson law. A stochastic process x of t with integral valued state space associated with counting one by one of an event, such that as t increases, the cumulative count can only increase, is called a counting or Poisson process. Cox and Isam 1980 deal the subject exhaustively. Poisson process is such a process. Postulates for Poisson process. Roman letter 1. Independence. N of t plus h minus n of t. The number of occurrences in the interval t, t plus h is independent of the number of occurrences prior to that interval. Roman letter 2. Homogeneity in time. Pn of t, depends only on the length t of the interval and is independent where this interval is situated, that is, Pn of t gives the probability of the number of occurrences of e in the interval t1, t plus t1, which is of length t for every t1. Roman letter 3. Regularity. In an interval of infinite Simon length h, the probability of exactly one occurrence is lambda h plus order of h, and that of more one occurrences is of order of h. Occurrences are regularly or orderly. Order of h is used as symbol to denote a function h, which tends to 0 more rapidly than h. That is, as h tends to 0, order of h divided by h tends to 0. In other words, if the interval between t and t plus h is of very short duration h, then P1 of h equal to lambda h plus order of h. Summation k equal to 0 to infinity pk of h equal to order of h. Since summation n equal to 0 to infinity Pn of h equal to 1, it follows that P0 of h equal to 1 minus lambda h plus order of h. Under the postulates Roman letter 1, 2, 3, n of t follows Poisson distribution with mean, that is, Pn of t is given by the Poisson law. Pn of t equal to e power minus lambda t into lambda t power n divided by n factorial, n equal to 0, 1, 2, 3, etc. Inter-arrival time. With a Poisson process n of t, t greater than or equal to 0, that means inside the flower bracket, where n of t denotes the number of occurrences of an event E by epoch t, there is associated a random variable or the interval x between two successive occurrences of E. We proceed to show that x has a negative exponential distribution. Important statements. The interval between two successive occurrences of Poisson process n of t, t greater than or equal to 0 inside the flower bracket having parameter lambda as a negative exponential distribution with mean 1 by lambda. The interval between two successive occurrences of Poisson process are identically and independently distributed random variables which follow the negative exponential law with mean 1 by lambda. If the interval between successive occurrences of an event E are independently distributed with a common distribution with mean 1 by lambda, then the events E form a Poisson process lambda t. Interesting properties of Poisson process. We consider here some interesting properties which are of great use in the study of various phenomena. We have shown that the interval xi inside the bracket equal to ti plus 1 minus ti between two successive occurrences ei plus 1 I greater than or equal to 1 of a Poisson process with parameter as an exponential distribution with mean 1 by lambda. Further, the following results holds. For a Poisson process with parameter, the interval of time x up to the first occurrence also follows an exponential distribution with mean 1 by lambda for probability of x naught greater than x equal to probability of n of x equal to 0 equal to e inside the bracket x greater than 0. In other words, the relation 2, 1 does not depend on I or on ti. The same argument also leads to another very important property. Suppose that the interval x is measured from an arbitrary instant of time ti plus gamma in the interval ti, plus 1 and not just the instant ti of the occurrence of ei, and y is the interval up to the occurrence of ei plus 1 measured from ti plus gamma, that is y equal to ti plus 1 minus ti plus gamma. Y is called random modification of x or residual time of x. It follows that Roman letter 2. If x is exponential, then its random modification y has also exponential distribution with the same mean. We may state the result also as follows. Roman letter 3. For a Poisson process with parameter lambda, the interval up to the occurrence of the next event measured from any start of time, not necessarily from the instant of the previous occurrence, is independent of the elapsed time, since the previous instant of occurrence and is random variable having exponential distribution with the mean 1 by lambda. Example. Suppose that E and F occur independently and in accordance with the Poisson process with parameters A and B respectively. The interval between two consecutive occurrences of F is the sum of two independent exponential distribution and thus as density f of x equal to b square into x into e power minus bx, x greater than 0. The probability that k occurrences of E take place between every second occurrence of F is given by integral 0 to infinity e power minus at into at power k divided by k factorial into b square into t into e power minus bt into dt equal to a power k into b square divided by k factorial into integral 0 to infinity e power minus of a plus b into t power k plus 1 into dt equal to a power k into b square divided by k factorial into gamma k plus 2 divided by a plus b whole power k plus 2 equal to k plus 1 into b divided by a plus b the whole square into a divided by a plus b the whole power k equal to k plus 1 c1 into b by a plus b the whole square into a by a plus b whole power k, comma, k equal to 0, 1, 2, etc. The distribution is negative binomial. This also follows from the fact that we have here a sum of two independent geometric distributions. Random walk. A random walk is a mathematical formalization of a path that consists of a succession of random steps. For example, the path traced by a molecule as it travels in a liquid or a gas, the search path of a foraging animal, the price of a fluctuating stock, the financial status of a gambler can all be modeled as random walks. Although they may not be truly random in reality, the term random walk was first introduced by Carl Pearson in 1905. Random walks have been used in many fields: ecology, economics, psychology, computer science, physics, chemistry, and biology. Random walks explain the observed behaviors of many processes in these fields and they serve as a fundamental model for the recorded stochastic activity. Various different types of random walks are of interest. Often, random walks are assumed to be Markov chains or Markov processes, but other more complicated walks are also of interest. Some random walks are on graphs, others on the line, in the plane, in higher dimensions, or even curved surfaces. While some random walks are on groups, random walks also vary with regard to the time parameter. Often, the walk is in discrete time and indexed by the natural numbers as x0, x1, x2, etc. However, some walks take their steps at random times, and in that case, the position xt is defined for the continuous of time t greater than or equal to 0. Specific cases or limits of random walks include the Levy flight. Random walks are related to the diffusion models and are a fundamental topic in discussions of Markov processes. Several properties of random walks, including dispersal, distributions, first passage times, and encounter rates, have been extensively studied. Lattice random walk. One-dimensional random walk. An elementary example of random walk is the random walk on the integer number line z, which starts at 0 and at each step moves +1 or -1 with equal probability. This walk can be illustrated as follows. A marker is placed at 0 on the number line and a fair coin is flipped. If it lands on heads, the marker is moved 1 unit to the right. If it lands on tails, the marker is moved 1 unit to the left. After 5 flips, the marker could now be on 1, -1, 3, -3, 5, or -5. With 5 flips, 3 heads and 2 tails in any order will land on 1. There are 10 ways of landing on 1 by flipping 3 heads and 2 tails. 10 ways of landing on -1 by flipping 3 tails and 2 heads. 5 ways of landing on 3 by flipping 4 heads and 1 tail. 5 ways of landing on -3 by flipping 4 tails and 1 head. 1 way of landing on 5 by flipping 5 heads. And 1 way of landing on -5 by flipping 5 tails. See the figure below for an illustration of the possible outcomes of 5 flips. To define this walk formally, take independent random variables z1, z2, etc., where each variable is either 1 or -1 with a 50% probability for either value, and set s0 equal to 0 and sn equal to summation j equal to 1 to n zj. The series Sn is called a simple random walk on Z. This series, the sum of sequence of -1s and 1s, gives the distance walked. If each part of the walk is of length 1, The expectation E of Sn, that is called expectation of Sn of Sn, is 0, that is the mean of all coin flips approaches 0 as the number of flips increases. This follows by the finite additivity property of expectation. Expectation of Sn equal to summation j equal to 1 to n, expectation of Zj equal to 0. A similar calculation using the independence of the random variables and the fact that expectation of Zn square equal to 1 shows that expectation of Sn square equal to summation I equal to 1 to n, summation j equal to 1 to n, expectation of Zj into Zi equal to n. This hints that expectation of modulus of Sn, the expected translation distance after n steps should be of the order square root of n. In fact, limit n tends to infinity, expectation of modulus of Sn divided by square root of n equal to square root of 2 by pi. This result shows that diffusion is ineffective for mixing because of the way the square root behaves for large n. How many times will a random walk across a boundary line if permitted to continue walking forever? A simple random walk on Z will cross every point an infinite number of times. This result has many names: the level crossing phenomenon, recurrence, or the gambler's ruin. The reason for the last name is as follows: a gambler with a finite count of money with eventually loss when playing a fair game against a bank with an infinite amount of money. The gambler's money will perform a random walk and it will reach 0 at some point and the game will be over. If A and B are positive integers, then the expected number of steps until a one-dimensional simple random walk starting at 0, first it's B or minus A is AB. The probability that this walk will hit B before minus A is A divided by A plus B, which can be derived from the fact that simple random walk is martingale. Some of the results mentioned above can be derived from properties of Pascal's triangle. The number of different walks of n steps where each step is plus 1 or minus 1 is 2 power n. For the simple random walk, each of these walks are equally likely. In order for Sn to be equal to a number k, it is necessary and sufficient that the number of plus 1 in the walk exceeds those of minus 1 by k. The number of walks which satisfy Sn equal to k is equally the number of ways of choosing n minus k divided by 2. With n is the number of allowed moves denoted n minus k divided by 2. For this to have meaning, it is necessary that n and k be even numbers. Therefore, the probability that Sn equal to k is equal to 2 power minus n into n minus k divided by 2. By representing entries of Pascal's triangle in terms of factorials and using Stirling's formula, one can obtain good estimates for these probabilities for large values of n. If the space is confined to Z plus, for brevity, the number of ways in which a random walk will land on any given number having 5 flips can be shown as 0, 5, 0, 4, 0, 1. We have written in the flower bracket. This relation with Pascal's triangle is demonstrated for small values of n. At 0 turns, the only possibility will be to remain at 0. However, at 1 turn, there is one chance of landing on minus 1 or one chance of landing on 1. At 2 turns, a marker at 1 could move to 2 or back to 0. A marker at minus 1 could move to minus 1 or back to 0. Therefore, there is one chance of landing on minus 2, 2 chance of landing on 0 and 1 chance of landing on 2. Now we are going to see the Pascal's triangle. The values of k are minus 5 to plus 5. what are all values having between minus 5 to plus 5 means we have minus 5, minus 4, minus 3, minus 2, minus 1, 0, 1, 2, 3, 4, 5. The central limit theorem and the law of the iterated logarithm describe important aspects of the behavior of simple random walks on Z. In particular, the former entails that as n increases, the probabilities proportional to the numbers in each row approach a normal distribution. As a direct generalization, one can consider random walks on crystal lattices, infinite fold abelian covering graphs, or finite graphs. Actually, it is possible to establish the central limit theorem and a large deviation theorem in the setting. As a Markov chain, a one-dimensional random walk can also be looked at as a Markov chain whose state space is given by the integers I equal to 0, plus or minus 1, plus or minus 2, etc. For some number p satisfying 0 less than p less than 1, the transition probabilities, the probability Pij of moving from state I to state j are given by Pi, I plus 1 equal to p equal to 1 minus Pi, I minus 1. Higher dimensions. Imagine now a drunkard walking randomly in an idealized city. The city is effectively infinite and arranged in a square grid, and at every intersection, the drunkard chooses one of the 4 possible routes, including the one he came from with equally probability. Formally, this is a random walk on the set of all points in the plane with integer coordinates. Will the drunkard ever get back to his home from the bar? This is the two-dimensional equivalent of the level crossing problem discussed above. It turns out that he almost surely will in a two-dimensional random walk, but for 3 dimensions or higher, the probability of returning to the origin decreases as the number of dimensions increases. In 3 dimensions, the probability decreases to roughly 34%. The trajectory of a random walk is the collection of sites it visited considered as a set with disregard to when the walk arrived at the point. In 1 dimension, the trajectory is simply all points between the minimum height of the walk achieved and the maximum. Both are on average, on the order of square root of n. In higher dimensions, the set has interesting geometric properties. In fact, one gets a discrete fractal, that is a set which exhibits stochastic shelf similarity on large scales, but on small scales one can observe jaggedness resulting from the grid on which the walk is performed. The 2 books of Lauer referenced below are a good source on this topic. Stationary processes. Second order processes. We consider here real valued stochastic processes in continuous time. A stochastic processes x of t, t belongs to capital T, that means inside the flower bracket, is called a second order processes if expectation of x of t the whole square less than infinity. It is called the collection of second order random variables. The mean function is defined by m of t equal to w of x of t, and the covariance function is defined by c of s t equal to covariance of x of s x of t equal to expectation of x of s into x of t minus expectation of x of s into expectation of x of t. The notation cs t is also used instead of c of s t. A covariance function satisfies the following properties. Number 1, it is symmetric in t and s, that is c of s t equal to c of t s, where s t belongs to capital T. Number 2, application of Schwarz inequality yields c of s t less than or equal to square root of C of S comma S into C of T comma T. Number 3. It is non-negative definite, that is, we have to write summation j equal to 1 to n, again summation j equal to 1 to n aj into ak into C of Tj comma Tk equal to expectation of summation j equal to 1 to n aj into xtj whole square greater than or equal to 0, where a1, comma, etc. an is a set of real numbers and ti belongs to capital T. Number 4. Closure properties. The sum and product of two covariance functions. Stationary. A second order process is called covariance stationary or weakly stationary or wide sense stationary if its mean function m of t is independent of t and its covariance function c of s comma t is a function only of the time difference modulus of t minus s, comma, for all t comma s, that is c of s comma t equal to f of t minus s. This also implies that for any t naught, c of s plus t naught, comma, t plus t naught equal to covariance of x of s plus t naught, comma, x of t plus t naught equal to covariance of x of s, comma, x of t, and then equal to c of s comma t. If for arbitrary t1, comma, etc. till tn the joint distribution of the vector random variables, then x of t1, comma, x of t2, etc. x of tn and x of t1 plus h, comma, etc. x of tn plus h are the same for all h greater than 0, comma, then the stochastic process x of t, comma, t belongs to capital T is said to be stationary of order n. It is strictly stationary if it is stationary of order n for any integer n. Stationary of a process implies that the probabilistic structure of the process is invariant under translation of the time axis. Many processes encountered in practice exhibit such a characteristic. Now for such a strictly stationary process, comma, the statistical properties of the associated joint distribution of x of t1 plus h, comma, etc. x of tn plus h will obviously be independent of h. This will hold in particular in case of the moments of the distribution, comma, when this exists. If the mean of the process x of t exists, comma, then expectation of x of t must be equal to expectation of x of t plus h for any h, so that expectation of x of t must be a constant m independent of t. Without loss of generality, we shall assume that m is 0 if moreover the covariance function c of s comma t exists, then c of s comma t equal to covariance of x of t comma x of s equal to expectation of x of t comma x of s equal to expectation of x of t plus h comma x of s plus h, and then equal to expectation of x of t minus s into x of 0. This shows that c of s comma t is a function of the time difference modulus of t minus s. Higher moments, when this exists, can also be considered. Many of the important questions relation to a stochastic process can be adequately answered on the basis of knowledge of the first two moments of the process. Note that a strictly stationary process will not necessarily be a weakly stationary process, comma, nor will a weakly stationary process be necessarily strictly stationary. A process which is not stationary is said to be a non-stationary. The process considered will be assumed to be real throughout. We now define a class of stochastic process in terms of an important specific distribution - normal distribution. Stochastic processes. Since the last century, there have been marked changes in the approach to scientific enquiries. There has been greater realization that probability models are more realistic than deterministic models in many situations. Observations taken at different time points rather than those taken at a fixed period of time began to engage the attention of probabilistic. This led to new concept of indeterminism in dynamic studies. This has been called dynamic determinism. The period of dynamic determinism began roughly with the work of Mendel. The physicist played a leading role in the development of dynamic determinism. Many a phenomenon occurring in physical and life sciences are studied now not only as a random phenomenon but also as one changing with the time or space. Similar considerations are also made in other areas such as social sciences, engineering and management and so on. The scope of applications of random variables which are functions of time or space or both has been on the increase. Families of random variables which are functions of say time are known as stochastic processes. Example: consider a simple experiment like throwing a true die. Example 1. Suppose that xn is the outcome of the nth row, n greater than or equal to 1. Then xn, n greater than or equal to 1, we will write inside the flower bracket is a family of random variables such that for a distinct value of n equal to 1, 2, 3, one gets a distinct random variables xn inside the flower bracket xn, n greater than or equal to 1 constitutes a stochastic process known as Bernoulli process. Example 2. Suppose that xn is the number of sixes in the first nth rows for a distinct value of n equal to 1, 2, etc. We get distinct binomial variable xn inside the flower bracket xn, n greater than or equal to 1, which gives a family of random variables is a stochastic process. Example 3. Suppose that xn is the maximum number shown in the first rows. Here xn, n greater than or equal to 1 that has been inside the flower bracket constitutes a stochastic process. Consider that there are R cells and infinitely large number of identical balls, and that balls are thrown at random one by one into the cells, the ball thrown being equally likely to go into any one of the cells. Suppose that xn is the number of occupied cells after n throws, then inside the flower bracket xn, n greater than or equal to 1 constitutes a stochastic process. Consider a random event occurring in time such as number of telephone calls received at a switchboard. Suppose that x of t is the random variable which represents the number of incoming calls in an interval 0, t, that means in the open interval 0, t of duration t units. The number of calls within a fixed interval of specified duration, say 1 unit of time, is a random variable x of 1, and the family x of t, t belongs to capital T constitutes a stochastic process t equal to 0, infinity. Specification of stochastic process. The set of possible value of single random variable xn of stochastic process xn, n greater than or equal to 1 is known as its state space. The state space is discrete if it contains a finite or denumerable infinity of points, otherwise it is continuous. For example, if xn is the total number of sixes approaching in the first nth rows of a die, set of possible values of xn is discrete. We can write xn equal to yn plus etc till yn, where yi is a discrete random variable outcome of the ith row, and yi equal to 1 or 0 according as the ith row shows 6 or not. Secondly, consider xn equal to z1 plus etc. zn, where zi is the continuous random variable assuming values in closed interval 0, infinity. Here, the set of possible values of xn in the interval, that means in the closed interval 0, infinity, and so that state of xn is continuous. In the above two examples, we assume that the parameter n of xn is restricted to the non-negative integers n equal to 1, 2, etc. We consider the state of the system at distinct time points n equal to 0, 1, 2, etc. only. Here, the word time is used in wide sense. We note that in the first case considered above, the time n implies row number n. On the other hand, one can visualize a family of random variables xt, t belongs to capital T. We have to write inside the flower bracket, or x of t, t belongs to capital T. This also want to write inside the flower bracket. Such, the state of the system is characterized at every instant over a finite or infinite interval. The system is then defined for continuous range of time, and we say that we have a family of random variable in continuous time. A stochastic process in continuous time may have either a discrete or a continuous state space. For example, suppose that x of t gives the number of incoming calls at a switchboard in an interval 0, t, that means it's in open interval. Here, the state space of x of t is discrete. X of t is defined for a continuous range of time. We have a process in continuous time having a discrete state space. Suppose that x of t represents the maximum temperature at a particular place in 0, t, then the set of possible values in x of t is continuous. Here, we have a system in continuous time having a continuous state space. So far, we have assumed that the values assumed by the random variable xn or x of t are one-dimensional, but the process xn, that means inside the flower bracket, may be multidimensional. Consider x of t equal to x1 of t, x2 of t inside the bracket, where x1 of t represents the maximum and x2 of t the minimum temperature at a place in an interval of time 0, t in the open interval. We have here a two-dimensional stochastic process in continuous time having continuous state space. One can similarly have multi-dimensional processes. One-dimensional processes can be classified by following four types of processes. Number 1, discrete time, discrete state space. Number 2, discrete time, continuous state space. Number 3, continuous discrete state space. Number 4, continuous time, continuous state space. All the four types may be represented by x of t, t belongs to capital T, that means inside the flower bracket. In case of discrete time, the parameter generally used in n, that is, the family is represented by xn, n equal to 0, 1, 2, etc. inside the flower bracket. In the case of continuous time, both the symbols xt, t belongs to capital T inside the flower bracket and x of t, t belongs to capital T inside the flower bracket are used. The parameter t is usually interpreted as time, though it may represent such characters as distance, length, thickness, and so on. Some authors call the discrete parameter family a stochastic sequence and the continuous parameter family a stochastic process. We shall use here the notation x of t, t belongs to capital T inside the flower bracket both in the case of discrete and continuous parameter and shall specify capital T whenever necessary. relationship. In some cases, the random variable xn, that is, members of the family xn, n greater than or equal to 1 inside the flower bracket are mutually independent, but more often they are not. We generally came across processes whose members are mutually dependent. The relationship among them is often of great importance. The nature of dependence could be infinitely varied. Here, dependence of some special types which occurs quite often and is of great importance will be considered. We may broadly describe some stochastic processes according to the nature of dependence relationship existing among the members of the family. Processes with independent increments. If for all t1, etc. tn, t1 less than, t2 less than, etc. less than tn, the random variables x of t2 minus x of t1, x of t3 minus x of t2, etc. x of tn minus x of tn minus 1 are independent, then x of t, t belongs to capital T, that means we have to write inside the flower bracket, is said to be a process with independent increments. Suppose that we wish to consider the discrete parameter case, consider a process in discrete time with independent increments, writing t equal to inside the flower bracket 0, 1, 2, etc. ti equal to I minus 1, where x of ti equal to xi minus 1, zi equal to xi minus 1, where I equal to 1, 2, etc. and z0 equal to x0. That means we call it as z0 equal to x0. We have a sequence of independent random variables zn, n greater than or equal to 0. We have written in the flower bracket. Conclusion. In this chapter, we have covered the following in detail: stochastic processes and specifications, stationary processes, Markov chains, Markov processes, Poisson process, renewal process, birth and death process, random walk, Brownian motion.